and I conditioned it, and then you were doing.
That's one of the many things I was doing. One of the many things I was doing. So, so let's talk about extrema. So what's our math definition of extrema,
Should
right?
show people that slideshow with no context whatsoever.
With no context, yeah, they're gonna wonder what that's all about. So, extrema for us in math, if f is some function that's defined on an interval I, right? And when we say an interval I, it's just some values of x that we're specifying. Typically, when we talk about an interval I, usually we'll say something like this. Like an interval I might be, we'll talk about the endpoints. So an interval I could be, for example, something like that maybe, where A is the left endpoint and B is the right endpoint. And that would be our interval I. All we specify here is that it has to contain some point C on this interval. We haven't specified what it is, but on this interval, we would say that f of C is the minimum of the function on our interval if this is always true. If f of C is less than or equal to f of x for all other values of x in that interval. Okay, can you see that that's kind of our really exacting mathematical way of saying it's the lowest point, right? That's really all it's saying, isn't it? It's the smallest value of the function on this interval, okay? And likewise, we'd say f of C is the maximum of f on I if for all x in the interval, f of C is greater than or equal to f of x. In other words, it's the biggest point, the biggest value in our interval, okay? But here's where it gets a little bit, that in and of itself is no big deal. You've seen maxima and minima before lots of times. We talked about them in Algebra 2 a couple years ago, right? But we're going to get more precise with it. So the minimum and maximum of a function on an interval are the extreme values, or the extrema. That's the plural. Singular form of extrema is extremum, right? You talk about a singular extremum or multiple extrema. The minimum and maximum of a function on an interval could be called different things, though. We could talk about absolute extrema, or global extrema, or relative extrema. And they mean related but different things, subtly different things, right? Say it again. That's fine. So here's some examples. Like, look, we'll come back to these, but let's just look at a couple examples. So what about something like this? If we want to talk about the interval, let's say it's going to be the closed interval from -1 to 2. So we've got this function, f of x equals x squared plus 1, just a parabola, right? Regular old parabola that's been vertically translated by 1, okay? Well, let's only graph that function on our interval from -1 to 2 inclusive. It's a closed interval. Remember, that means we're including the endpoints, right? Okay, so does it make sense then that the point 2,5 is that represents a maximum of the function, right? 5 is the maximum value of the function. We could say that that is our absolute maximum, the biggest value of the function. Does it also make sense that 0, 1 represents the minimum of the function? We talked about this in Algebra 2, right? No big deal, nothing earth-shattering there at all. Okay, but try this one. So what if we change the interval? What if the interval becomes an open interval instead? So now we're not including the endpoints, okay? The point 0, 1 is still the minimum of the function, right? It is the lowest point, but there is no maximum. You get that? It's a weird concept.
Wouldn't it be a point that's infinitesimally close to
What point
5?
is that? See what I'm saying? That's not a point. That's a limit, right? It's a limit. So you could say, sure, we could say that the maximum of the function approaches 5, right? But it's not 5. There isn't a point that I can say, aha, that's the maximum, and so 1 does not exist. As soon as you think you're at the point next to that open circle, open endpoint, well, in fact, you've still got an infinite number of them between you and the endpoint, don't you? You can never get there. And we'll go back, I don't know how, I'm probably going to wear half of the carpet here doing this example, but if I cut my distance to the door in half every second, remember, I never get to the door, right? It's always my limit of my motion, but I never get there. I take an infinite number of steps and never get there. If I can subdivide space mathematically, right? If I could subdivide space infinitely, yes?
It's called Newton's paradox.
Right, but you get the idea, right? I mean, we get this notion that we can't have a maximum there. Likewise, we could do something like this, right? We could redefine the function a little bit as, let's say, a piecewise function, where g of x is going to equal, no longer is it f of x, g of x equals the parabola we've been talking about, x squared plus 1, when x is not equal to 0. So for all values except 0, but at x equals 0, let's redefine the function as having a value of 2. So in other words, we just created a hole in the parabola and a point at 2 instead, right, at 0, 2. Yes, sir?
If the point were below the parabola, that becomes minimum.
It would become the minimum.
Okay.
Yeah, it would be the absolute minimum, okay? But in this case, we have neither a minimum nor a maximum. Actually, in this case, we do have a maximum, don't we? Because I guess we redefined, if we move down a little bit here, we called this a closed interval again, right? And so now the endpoints are included, and so yeah, this is a maximum, but there is no minimum. Okay, you get the idea? Okay, so let's focus. Okay, so extreme value theorem. This is covered in your book, but I want to just touch on this very briefly. Make sure this makes sense. Ooh, that doesn't look very good. Let me fix one thing on this. I don't like the way that looks. Let's do that. And that. Now it looks better. Okay. So if f is continuous on a closed interval from a to b, then f has both an absolute minimum and an absolute maximum on the interval. Guaranteed. If the function is continuous, now just think back, this is good review. You'll find in calculus we're constantly reviewing because we constantly draw on earlier concepts, which is one of the reasons I love calculus. What's it mean to be continuous? What's our working definition of a continuous function in terms of like my pen and the board? Never comes off the board, right? And if it's a function, I can't violate the vertical line test, right? So I defy you to get from, we'll call this, so here's A, and there's B, and let's say here's the point A, f of A, and here's the point B, f of B. There is no way that you can get from there to there without going through a point that you could definitely call the highest point, and without going through a point that you could call the lowest point, right? I could do this, and it's pretty simple, right? Then the highest point is that end point, the lowest point is that end point. I could take a different path. I could go like, well, I didn't do it. Like that. And then I could say that that's the minimum, right? These two might even be a shared maximum. Maybe they have the same y value, but still, it's a tie then. They still both are considered a maximum, right? That make sense? You might even think, well, what if I were gonna, okay, I'll get you this, right? What if we're gonna do this? What if we're gonna say our function does something like this instead? What if it goes from there to there, and it's horizontal, just a horizontal line? Then it's an infinite tie. We have an infinite number of points that act as the minimum and also act as the maximum, right? Every point on that line is the highest point and the lowest point on the interval at the same time. That's not a very exciting case to consider. You know, it's just kind of we would never really think about that one in this context because it's so boring, right? As you'll see as we move on with this stuff, we're more interested in places like that, right? Or even the endpoints, right? Okay, so we've got the extreme value theorem. You know we have to have extrema on a closed interval if it's continuous. Now let's get more specific about the different kinds of extrema we're going to look for. Okay, so the first one that we're really going to focus on is a relative, or sometimes it's called a local extremum. Okay, so it could be a maximum or a minimum, right? And here's our definition. If there's an open interval, and it could be closed, right? But a closed interval contains an open interval. Does that make sense? Think about that statement. If I talk about the closed interval, I'll come back to that. The closed interval from A to B is really just equal to the endpoint A plus the open interval from A to B plus the endpoint B, right? So there's two extra points on the closed interval, but it contains the open interval also, right? So the open interval plus the endpoints are added. Makes sense, right? Okay, so if there's an open interval containing C on which f of C is a maximum, then we say f of C is called a relative maximum. That's simple. Okay, so what's that mean? If I've got a complicated looking function, I'm just going to add a picture here. So what if I've got some complicated looking function? It has lots of stuff going on. And we're just going to look on the open interval from A to B. Don't like it. Something like that. Where's an example of a relative minimum? Where's one?
The point adjacent, almost adjacent to
Okay, so, which, like this one?
A. Yes.
Yeah, so relative minima there's one. There's another one.
Every drop.
Ah, okay. There and there, right? This is the lowest of the relative minima, but they're all relative minima. How come? Because on some, I can always define some interval on which each of these points is the smallest. It doesn't have to be the interval from A to B. I can pick a smaller interval, right? I could pick this interval just right here. I could maybe just look at that part right there. Okay, I could look at just that part right there, or just that part right there. And those are the smallest values on each of those open intervals. If there's any open interval on which a point represents a minimum, then it's a relative minimum, okay? Relative to what? Well, the points around it, right? That's why we call it a relative minimum. It doesn't mean that it is the lowest point. It just means it's the lowest point relative to the territory around it. In math, we'd say relative to the neighborhood of values around it, okay? So where are some relative maxima? Well, obviously, I mean, those are going to be what? On this, geographically, those are the peaks, aren't they? So there and there, I guess, are my relative maxima. Okay, make sense? So yeah, we can say that essentially a relative maximum is plain and simple a peak in the function. It looks like a mountaintop. A relative minimum is a valley. That's what they are. Okay? Relative to the points immediately around them, they are the lowest or the highest points. Okay? Okay, so let's talk about the types of relative extrema. So we're looking for peaks and valleys. Sure. Right there?
No, the one for that.
That one right there?
Yeah.
Okay.
Okay.
Okay. Okay, types of relative extrema. So what about function like this? let's just take this function right here. Here's f of x, 9 times the quantity x squared minus 3 over x cubed. Okay, can you see a relative extremum on that graph?
Yeah.
There's kind of a peak there, right? On Desmos, this is kind of nice. If I click on the function, either up here, or if I click on the function down here, you notice what it does, and I'm sure we've mentioned this before, but it gives you these light gray points at important places on the function. Why is this important? Because it's a maximum, because it's a relative maximum. Desmos does calculus pretty well. So the point 32 that represents a relative maximum, right? We could see, you know, if I were to draw a tangent line, that's what the tangent line looks like. So what is the value of the derivative? So if I do f prime of 3, right, if I evaluate the derivative of this function at 3, what's Desmos going to tell me? 0. Yeah. Everybody see that? Okay. So let me maybe take a picture of this for the notes. Oh, I'll do this. Okay. So we see there's one thing we could make a prediction here, right? This looks like maybe this is something general that's going to happen. If we have a function with a horizontal tangent, that's one kind of place where we could look for a peak, isn't it? Or a valley, for that matter. Could be a valley too, right? Okay? So places where the derivative is equal to 0. Okay, let's try another one. How about one like that? So now I've got my function f of x equals absolute value of x. Everybody agree there's a pretty obvious relative minimum
Yes.
right there?
But
It's not differentiable.
Okay, so what's Desmos going to tell me if I take the derivative at x equals 0?
Error.
It's actually going to tell me undefined. It's pretty smart, right? It tells me the derivative is undefined. That's another important discovery we've got there. And remind us why that's undefined, why the derivative is undefined there.
It's a short form.
Sharp corner, right? Remember, that's one of the places where we said derivatives are undefined. Okay? Right. Whereas here we had horizontal tangent line. Right? Okay. How about just look at maybe one more quick example. And this is like the first one, isn't it? Right? If I've got a sine curve, you can tell me, obviously there's going to be a relative maximum, that's a peak, and there's an example of a valley, right? And so as expected, those give me horizontal tangent lines, right? If I evaluate the derivative at pi halves, I should get 0, shouldn't I? Right? And if I evaluate the function at 3 halves pi, I also get 0. Okay? So let's capture those. I'll take a picture for our notes. Will that fit? Well, it's gonna have to fit. Okay, so we could summarize this then, right? We've got these different, we saw different types of peaks and valleys there, right? We saw a sharp peak, and that's representative of one flavor of extremum, and we saw a smooth rounded peak, okay? We could also see the same thing, and this was an example where we had an absolute value function. Here's an example where the derivative was undefined because we had a sharp corner, and here's an example where the derivative equaled 0 at C, right? We had a horizontal tangent line. And of course, we can see the same thing for valleys, right? Okay, so this tells us something important. This gives us a new important definition. So we'd say that the places where curves do one of those two types of things, where they either have sharp peaks or valleys, or smooth peaks or valleys, we call those places critical numbers. Okay? And furthermore, we even figured out where we would look for those. At places where the derivative is equal to 0, those are places where we could have smooth peaks or valleys, right? So one species of critical number are all the places on an interval where the derivative is equal to 0. All the values of x where the derivative equals 0, okay? The other species of critical number that we'll look for would be all the values on an interval where the derivative is undefined, okay? But it's important to recognize that, well, not all critical numbers are going to give us extrema, right? So we could say that every extremum has to occur at a critical number, guaranteed, but not all critical numbers are going to yield extrema. Let's look at an example. Got another one here. Okay, let's go to number 4, I think it was, yeah. Okay, what about something like this? We got the function, I just made one up here, f of x equals the quantity x minus 1 cubed plus 1. Would you agree that there's a place, oh, it won't give me that. Huh, interesting. It won't give it to me because it's not a critical number. Okay, I'll buy that. Now it gives it to me because it's an intersection. But there's a place at the point where x equals 1, the derivative is equal to 0. I'll prove it to you. F prime of 1 is 0, right? And yet that's pretty clearly not a maximum nor a minimum, right? Neither a maximum nor a minimum. So that's a false alarm. Okay, later on in the class we'll call that an inflection point instead for reasons that we'll talk about later. But it's a false alarm on our search for critical numbers, or search for extrema. It's a critical number that failed the test. Let's take a picture of that. And Desmos makes this so much better. Okay, so we get some examples where it wouldn't have, well, I got one more too. I was going to show you one like this, an actual example of one like that. So what if I pull up example 5? So if I just take a function like a cube root instead of a cubic function, f of x equals quantity x minus 1 cube rooted, so to the 1/3 plus 1, wouldn't you agree that there is a place here where the function is undefined, right? At that point right there, at x equals 1, if I try to evaluate the derivative, it's undefined. Okay? How come it's undefined? How come? Because it's a vertical tangent, right? And you have vertical functions. A vertical line is not a function, right? So once again, there's a place where the derivative is undefined. Okay? So let's get a picture of that guy too. Don't want him to feel left out. let's put the page there. Okay, so in general, yeah, we've got places where we could have false alarms. We have places where we could have a horizontal tangent without an extremum, or we have places where the derivative could be undefined without an extremum too. That'll make more sense, and you'll understand why I brought this up when we actually start doing some problems where we're going to find relative extrema for a specific function. I don't think we'll get there today, but we'll see. Okay, so I threw one in. This isn't in the book. This is kind of a cool theorem. You fill in the blank for me here, though. So don't say it out loud. I want you to think about this. If f, function f, has a relative extremum at c, and f is differentiable at c, then what has to be happening? Just pause and think about it.
Or is it something?
Okay, so it'd have to be a horizontal tangent. So what could I say about the value of the derivative at c?
0.
It's got to be 0, doesn't it? Right? It's hard to see that prime, but there's prime there, right? That prime of c equals 0. Let me make that prime more obvious, or primal. There. Okay? Okay, so we got the idea of relative extrema, peaks and valleys. We even can kind of start to think about how maybe our strategy is going to be, probably not today, but next week, when we start to go searching for relative extrema. If we have a function, we're just going to look for places where the derivative does one of two things. What are the two things we're looking for? Where the derivative either equals 0, those are candidates, right? Or it's undefined. Now, not all those may work out to be relative extrema, but that's our list we'll have to test, right? Test all those points. And I've got some really cool, of all the things I would say that my calc students do here, that when they go to college, the thing I always get feedback on, they say this was really helpful, was a way that you can pull all this together into a graphical approach. So I'm going to teach you a way to do this that I think is really, really useful when you get into like even higher level calculus, multidimensional calculus. This table method I'm going to show you, I'm sure probably other people do it in a similar way, but this is the way I've just kind of developed it over 25 years, and I really like the way this works. Okay, so now let's summarize this stuff, right? So relative extrema are peaks and valleys. Absolute extrema are, what are those? Absolute extrema, we never really pinned that definition down. Absolute extrema are the maximum. It's the maximum value. Maybe there's some ties. Maybe there's multiple values. And the minimum value, possibly there's a tie for that too, on a specific interval. So we're going to define an interval, and on that interval we could say, and I'll take you back to is this stuff, right? We could say, yes, that's an absolute minimum on this interval. It is the lowest point on this specific interval, right? So that's an absolute minimum. This is an absolute maximum. Is that a relative maximum?
No.
I'd say no. I mean, and here's the other frustrating thing about calculus is some textbooks would say, yeah, it is if it's an endpoint, but it's not. To me, it's not a pure. It's not a pure relative extremum because it's not a place where it doesn't fit the criteria, right? It doesn't fall at a critical level.
Because it's a parallel function, so it has no global.
Well, it's no. We haven't defined it yet. It does. But we'd say this is not a relative maximum because it's not a place where the derivative is either undefined or equal to 0, right? So for now, at least, we're gonna say no. We're talking about this in the purest form. That is not a relative maximum. This is a relative minimum, though, isn't it? So it's both absolute and relative, right? How about here? In this case, that is not an absolute maximum, but this one is, right? This one right here is still both relative and absolute. And then if we go down to this guy down here, all this is nothing, right? It's not a minimum at all. And this one is just absolute. Okay, so what about global?
Oh, yeah?
Yeah.
If you go back to that page.
To this page?
Yeah.
Yep.
Go down to the last example.
Mm-hmm.
that point, it's just sticking out there, is that a relative maximum?
It's one of those that's hard to, it's kind of hard to characterize. We could debate this. What's the argument for it being a relative maximum? Relative to its neighboring points, it's the highest. What's the argument against it? Well, can we give me an argument against it being a relative
That's not the
maximum?
It's
It's okay.
It's a discontinuity.
It's a discontinuity, but I guess, really technically, it's a discontinuity, and so the function's defined there, but the derivative is not, right? So it really honestly fits that criteria too. You almost never would talk about that point, and it should say something that I'm kind of having to have this debate internally and externally, because that's not a point you'd ever even talk about it as being a relative extrema, right? When you're talking in real life and when we look at functions and finding relative extrema, we're looking at continuous intervals, right? Where the functions continue, and that's the part where you might say, well, it's not a continuous and it's a piecewise function, so you're cheating, right? Okay, but how about this last term, real quick, just make sure we get this before we go. So absolute means it's the maximum or minimum value on a specific interval. What about a global extreme?
The entire function.
Yeah, the entire function. So the entire function on its complete natural domain, meaning the biggest domain it could possibly have. So the natural domain for example, for this function, and there's my function, f of x equals x squared plus 1. What's the natural domain of that function? All reals, right? There's no reason I could plug any value of x into that, and I'm going to get back an output, aren't I? So on the entire function, is there a global maximum, a global minimum? Yeah, right there, isn't it? Because this function always is going to go up in either direction from that one point. And so we could add that this is an example of a global minimum as well, okay? It's the only one, though. Right? Okay, so a global minimum would have to, out of necessity, it would have to be, well, what would be a weird example? Like, what if we took something like this?
A circle.
Not a function, right? But what if we took, for example, the absolute value of x? There's the function f of x equal, not absolute value, square root of x. Okay, its natural domain is what?
All positive reals.
No.
Greater than 0.
So all non-negative reals, right? So the natural domain of this would be that, correct? Right, so does this have a global minimum?
Yes.
Yeah, it's right there, isn't it? Is that also a relative minimum? There's the dilemma you have, right? I mean, is it or isn't it?
Yeah.
So you could say, and this is one where you kind of have to specify at the beginning, is it or isn't it? Are you going to consider it or are you not? I would say this one in a way is, because this is the entire global natural domain of the function. So you can't go to the left at this point. So for that reason, it kind of counts as a valid, because it's the end of the universe for this function. It's a subtle point, but you see the difference? Okay.
So in the case of that function with the single point defined, is the reason